Okay, so we talk about quicksort analysis of quicksort. So before that, let us just write the pseudocode for quicksort. So for quicksort, we need to call the partition algorithm. So if we just run the quicksort of an array which is starting from P to Q. Now, if P is equal to 1, P is equal to Q, then done, then stop, because that is the return, only one element that is already sorted. So, we stop at when P, this is the stopping condition every branch. Otherwise, else what we do? We call the partition. We call the partition on quicksort. We call the partition on this array, partition subroutine, which you have seen in the last class. So what it will do? It will just take this array and it will take this. This is as a pivot, first element. So this is A array. A is from P to Q. So what it is doing? It is putting the x in some position, and this is index is P, this is R, and this is Q. So it is putting x in the correct position, and it is returning the index of this where it is keeping this pivot element. So this is the partition. This is the partition subroutine is doing this. So this we have discussed in the last class, and this is a linear time algorithm. So we call the partition. So after calling the partition, it will divide into two subarray. This is left subarray, right subarray. Then again we have to call that is the divide step of the quicksort. Now again we have to call the quicksort on this subarray and this subarray, that is the concat step. So this is a recursive call. So we recursively call quicksort on the left subarray, again we recursively call quicksort on the right subarray. So that we have to write. So this is 4, we call recursively. So we have two quicksort call, quicksort on this left subarray. So that's why you have to return R to know what is the left subarray. So if we return R, then the left subarray is basically A P2 R minus 1. This is the left subarray, and another. So and right subarray, you have to call the quicksort on the right subarray also. So right subarray is basically index from R plus 1 to Q. So this is the left subarray and this is the right subarray. So again this is the concat step. Okay. So we sort this subarray, we sort this subarray. So this is the concat step. So this is the subroutine for quicksort, and the initial call is initially our array is 1 to n. So initial call is quicksort A 1 to n. This is the initial call of this quicksort. So initially our array is 1 to n. Slowly it will divide into subarray, then sub subarray. So the index will be in general P to Q. So that's why we kept the index P to Q. So after the initial call, it won't be 1 to n. So it will be some different index. So that's why we have we took the general index P to Q. Okay. So this is the pseudocode for quicksort. So now if we take an example. So if you take an example, so if you take say 6, 12, 13, 4, 5, 2, 9, 11. Suppose this is our input, and we have to apply quicksort on this. Okay. So on this input, what we do? So we first apply the partition algorithm. If we apply the partition algorithm, what it will? So it will partition the array into two parts. So 6, it will put 6 somewhere here, and it will divide into two parts. Left subarray, all the elements which are less than x will be left subarray. So they are basically 4, 5, 2, and all the elements which are greater than 6 will be in the right subarray. So they are basically 12, 13, 12, 13. So 4, 5, 2 are less than 6, 12, 13, 9, 11, and this is the index. This index is so this is 1, 2, 3, 4. So this is 4. So 4 will be returned from this partition algorithm, because this index we require to identify this subarrays. Otherwise, we cannot identify this subarrays. Na? If we return this 4, we know that up to 3 is the left subarray, and then after this 4 plus 1 to q is the right subarray. So again so this is the first call. Now again we have to call the quicksort on this. So if we call the quicksort on this, so 6 is in correct position. So again it will take this as a pivot. It will partition into 2 parts. So 4 will be sitting here, and all the elements over here is less than x, all the elements over here greater than x. So this is 6 is here, and again we call the quicksort on this. So this is basically the quicksort call partition on this. Again we call the quicksort. So this is the 12. So 12 will be sitting here, all the elements less than 12 will be here, 9, 11 and greater than 12. Now again we call the quicksort on this. So again we call quicksort on this, quicksort on this. There are only one element, so we stop. We call quicksort on this. So this will be again. So 9 will be there. So 9, 11. So 12, 13. So done. So this is basically a recursive call. This is basically a divide and conquer approach. So this is the example of quicksort. But here in our partition algorithm, we are choosing the first element as a pivot. Okay. So but we will see we can choose any one of this element as a pivot. So that we will see. So now we want to analyze this. We want to analyze this means we want to know the time complexity of this algorithm. So what is the time complexity of quicksort? To do the analysis, that is, quicksort analysis is much more interesting than the quicksort pseudocode. It will take much more time to analyze the quicksort than to know the what is quicksort. So that is more interesting, the quicksort analysis part. Okay, so we want to know the runtime of this. Runtime of quicksort. So that is the quicksort analysis, and for that we assume that all the elements are distinct in order to avoid this equality. To do this, we assume all the elements are distinct, and Tn we take the worst case runtime for quicksort. Worst case time complexity for quicksort. Okay. Okay, so now when is the worst case for quicksort? When is the worst case for this code? So worst case means, so if the partition is dividing the array into 0 is to n minus 1. So worst case will occur if we have a input as a sorted or reverse sorted array. So if the input is already sorted, if the input is sorted, then we are choosing the first element as a pivot. Then always the pivot element, in this case pivot is the minimum element. So pivot element is the minimum element always. So if the pivot is minimum element, if we choose the pivot is minimum, then after calling the partition, what will be the situation of the subarrays? If pivot is minimum, we know the pivot will be sitting somewhere here, all the elements greater than x will be here, all the elements less than x will be here. Now if pivot is minimum, then there is nobody which is less than x. So if pivot is a minimum, then the partition will give us this type of structure. So pivot will be sitting here, all the elements is greater than here. So this is 0 is to n minus 1 partition. So nobody is there in the left subarray, and n minus 1 element will be in the right subarray. So that is the situation if we choose the pivot to be minimum element among from the given array. And this will happen if we have a sorted array as a input. If the input is already sorted and we are choosing the first element as a pivot, so then it will partition 0 is to n minus 1, and again we call this quicksort on this. So, again we choose the first element as a pivot. So, that is the minimum among this. So, again it will be 0 is to n minus 1. So, throughout this execution it will be 0 is to n minus 1. So, in that case, so then what is the recurrence that case? So, if pivot is like this minimum, or if the pivot is maximum element, so that means if the input is say reverse sorted. So, we have to analyze this. So, suppose the input is reverse sorted. Reverse sorted means we have say if the input is like this 9, 8, 6, 5, 4, 2, 1. This is the reverse sorted input. If the input is reverse sorted and we are taking the first element as a pivot, then in this case the pivot will be the maximum element. Pivot is maximum element of the array. Now, if the pivot is maximum element, so how the partition will work? Then the partition will partition this into, so maximum means it has to be here and all the elements has to be less than here. So, it is basically n minus 1 is to 0. So, if the pivot is to be maximum or minimum, then it will be either 0 is to n minus 1 or n minus 1 is to 0. So, that means there is no the one part, it is subarray size is 0. So, that is why that is the worst case, we will come to that. So, if this is the situation, then we want to know what is the time complexity of this. So, that means we want to know the time complexity of this quicksort when the pivot is minimum or maximum. So, in that case, what is Tn? So, if Tn is the time for this quicksort, so this is taking theta of 1 time and this partition is taking theta of n. We know this linear time partition, that is the key point of the quicksort, and then we have a 2 recursive call of the same function quicksort. So, these 2 call, but we know pivot is here, we are taking pivot is minimum or maximum. So, we have one call is on 0. So, this is T0 and Tn minus 1 or Tn minus 1 and T0. So, in that case we have this recurrence. So, the time complexity for this, so Tn is basically sum of this theta of 1 plus theta of n plus T0 plus T of n minus 1 or T of n minus 1 plus T0. So, this will all be like theta of n plus T of n minus 1. So, this is basically T of n minus 1 plus theta of n. So, this is the recurrence for quicksort when the pivot is the maximum or minimum. Okay. And throughout the execution, if the pivot is maximum or minimum, in the first level we have given array 1 to n, we choose the minimum as a pivot. Okay. For our code we are choosing the first element as a pivot. So, we put this is sorted input. So, then this is the minimum, or if it is reverse sorted, this is the maximum. But for if we choose any element as a pivot element, so if that element is minimum or maximum always throughout the execution, even in the conquered step, then this will be the recurrence throughout the execution. Then we want to know the what is the time for this, what is the time complexity for this. So, to know this time complexity, what we do, we draw the recursive tree. This is the worst case recurrence. So, we draw the recursive tree. So, basically what we have, this is Tn is basically T0 plus Cn theta of n. T0 is just a symbolic notation. So, if you draw the recursive tree, Tn is basically Cn, this is T0, this is Tn minus 1. Now, again, now this is a problem of size n. n minus 1. Now, again we have to divide into sub problems, but again in the subsequent step, in the conquered step, we assume we are choosing the minimum or maximum as a pivot. So, that assumption has to be made in order to draw the recursive tree in this way. So, again this will be C of n minus 1 T 0 T of n minus 2 like this. So, again this is a problem of size n minus 1, again we further divide into sub problems, but again in that sub array we are assuming that again we are choosing the pivot to be minimum or maximum. So, in that case it will be again C of n minus 2 T 0 like this. So, this will continue until we stop T 0 or T 1. So, this is theta of 1. So, if the time is basically sum of this time. So, this is basically arithmetic series 1 n into n minus 1. So, this is basically C into n plus 1 by 2. This is basically order of n square algorithm. So, the solution for this is order of n square algorithm. So, this is the worst case. Okay. So, the time complexity is order of n square. This is the worst case, or we call this is as a unlucky case. So, what is the lucky case? When you get order of n log n algorithm, time is order of n log n, then we call this is a lucky case. So, this is an unlucky case. Okay. So, if we choose the pivot to be minimum or maximum, then this is a unlucky case. We are not lucky, we are unlucky if this is the solution of the recurrence. Okay. Now, when is the lucky case or when is the best case? So, best case may be, so we know that if the pivot is bad pivot in the sense if it is partitioning 0 is to n minus 1, that is called bad pivot. If our pivot is maximum or minimum for the corresponding input, then it is a bad pivot. So, that means it will partition. So, then what is the good pivot? So, that will give us a best case. So, what is the good pivot intuitively? If the pivot is partitioning the array into half half. So, that means if the pivot is, so we have given a input, if the pivot is partitioning into half half, pivot is sitting here, this is roughly n by 2, this is n by 2 minus 1. So, that is a floppiness we will do. So, that is lower ceiling or upper ceiling. So, this is this ratio n by 2 is to n by 2. Say then we say this is a good pivot. Why good? Because this will give us, we want to see what is the time complexity for this. So, if this is the situation, then what is our time complexity? What is the recurrence? T n equal to 2 T n by 2 plus theta of n. Because in that case, if pivot is sitting here, again we have to call quicksort for this, quicksort for this, but though these two have the same size n by 2 or n by 2 minus 1, that will be also n by 2 because of this is just a lower ceiling or upper ceiling. Okay. And this is the cost for partition and those initial steps. So, this is the recurrence for quicksort if the partition is n by 2 is to n by 2. Now, this recurrence we have seen, this is the same recurrence as merge sort. So, what is the solution? Again, if we use the master method, we can get this solution n log n. So, good. So, this is the lucky case, lucky. So, good pivot, best case, anything you can name. So, this is the best case scenario when the pivot is partitioning the array into two equal part, half half, n by 2 is to n by 2. Then our recurrence is just a, because we have to call again quicksort on this, quicksort on this. So, T of n by 2, T of n by 2. So, that is why 2 T n by 2 plus that is the cost for partition. So, this will give us the solution order of n log n. So, that is the lucky case. So, that is the best case. Okay. Now, suppose our pivot is not that much good, but little bit of good, in the sense it is not dividing the array into half half. It is just, and also it is not dividing into 0 is to n minus 1 like minimum or maximum. It is not the bad one. So, if it is little bit of lucky, so that is called almost best case. So, this will refer as almost base. Why it is almost base, we will come to know when we talk about the time complexity for this best case. So, almost best case means suppose our pivot is not that much good, but it is not even not worse than 0, the 0 is to n minus 1. Suppose our pivot is such that it is partitioning the array into two parts, one is say n by 10, another is say 9 n by 10, okay. Or maybe one is n by 100, another one 99 n by 100, okay. For simplicity n by 10, 9 n by 10. So, it will work for this also. So, that is the ratio 1 by 10, 9 n by 10. So, this ratio it is partitioning. So, pivot is such that it is partitioning in this ratio. For example, suppose say n is say 20. If n is 20, then how many elements are there? This is n by 10. So, this is 2 and this is x, if we keep, this is 17. So, this is only 2 elements. So, if we can assure that pivot is such that it is partitioning some little portion in any side, this could be this side also, it does not matter which side. So, if we can ensure that it is partitioning into two parts, then 0 is to n minus 1. So, if we can assure some little fraction in some of the part, then we will want to see what is the time complexity of this. So, if this is the situation, one part is said, then what is the recurrence? Then the recurrence will be T n is equal to, so this is the sub array, this is the right sub array, or it could be left or it could be right. So, then you have to call this quicksort on this, quicksort on this. So, this is basically T of, so T n is basically T of n by 10 plus T of 9 n by 10 plus theta of n, or basically this is the this is the partition cost C n. So, you want to know this is the recurrence for this case, almost base case, where the pivot is such that it will ensure that some fraction, maybe little fraction, some fraction will be there one sided and remaining will be almost all the elements will be other side. So, it is not 0 is to n minus 1, it is better than 0 is to n minus 1. Now, we want to know the solution for this. If it is giving us order of n log n, then we say this is a good pivot. Okay. So, in fact, this will give us order of n log n. So, that we have to see by the help of recursive tree. So, then we want to draw the recursive tree for this recurrence. So, our recurrence is T n is basically T of n by 10 plus T of 9 n by 10 plus C n. So, this is the recurrence, we have to solve the recurrence using the recursive tree. So, this is the problem of size n, we have two sub problems, one is T n by 10, T 9 n by 10. Now, again this is a problem of size n, so sorry size n by 2, n by 10. Now, again we will use the quicksort for solving this problem. Again we assume that our partition is partitioning this into 1 by 10 is to 9 by 10. So, this assumption is required. It is not that suddenly we assume here for this subsequent step we have best case, it is half half, then we have a different type of tree, but here we are assuming same recurrence will be go through. So, that means now this is a problem of size n by 10. So, again we call quicksort on this. So, again it will call the partition, again our partition will choose pivot, and that pivot is such that again it will be 1 by 10 is to 9 by 10 ratio. That is important, because it is not that suddenly in this step we will have half half, then we have different type of analysis. So, again this will be this is now size n by 10. So, this will be T of, so we just put n is equal to n by 10, n of 100, and this is basically T of 9 by 100, okay, and again this will be T of, so we put n is equal to 9 n by 10. So, this is 9 n by 100 and this will be 81 n by 100. So, this way. So, again this is a problem of size n by 100, and again we assume this is we will have the same recurrence, again our pivot is such that it will be 1/10 is to 9/10 ratio. So, if you do that, it will be basically C of that, C of that, C of that, C of that, and it will further reduce. So, when we stop at T1. So, which branch will end first? So, this ratio will end first, this will end first, this will reach to T1 soon. So, all the branches that this one. So, this will go little more because this is like this. So, we have branches over here, every branches will end to the T1. So, this will stop, we stop when we reach to the T1, and this is basically theta of 1, and this is basically theta of 1, and our time complexity is the sum of the all the nodes. So, to make the sum, we want to do the level wise sum. This is the first level sum, this is also Cn, this is also Cn. Again we can assume this is Cn, but this is not a inductive proof. So, that is why we need to take help of the recursive tree, substitution method to know the solution for this in a mathematical probable way. So, anyway, so this is Cn now. So, this is height of the tree is basically the order of log n base 2. If the height is h1 over here and if the height is h2 over here, we can simply say that so what is h1? h1 is basically n by 10 to the power h1 is 1, because that branch. So, h1 is basically log n base 10, but we can make it log n base 2 and 2 base 10. So, this is just a constant. So, height is order of log n. So, this side also height will be order of log n. So, basically time is, so if we have a complete tree like this, so it will be Tn is bounded by Cn h1 less than Tn less than equal to Cn h2. Okay. So, this is basically give us, because h1 and h2 are both order of log n. So, this is n log n. Lucky case, this is lucky, n log n is the lucky case. So, that is why it is called almost base. So, that is the thing. So, if our pivot is not half, if our pivot is such that it can assure that some fraction, some little fraction may be in one side remaining on the other side, then also we are lucky, then also this is the best case. So, that is why, so that we have to guarantee that. So, that is the that is why. So, if it is not even half, if it is just 1/10 is to 9/10, then also we are getting the lucky case, then also we are getting the best pivot. So, we will continue this analysis. So, we will talk about we analyze this if we are, suppose we are say we have 100 step to execute for a given array. Now, suppose in this 100 step we have 50-50 lucky unlucky. So, first suppose we are lucky, then next step we are unlucky, then lucky, then unlucky. So, 50-50 lucky unlucky situation, then we want to see whether ultimately we are lucky or unlucky. So, that analysis we will do in the next class. So, there we will see we will finally lucky. If we can assure some lucky step in the execution, then we are eventually we will be lucky. So, that analysis we will do in the next class. Thank you.